Now let's have a look at what we call the fundamental theorem of algebra. And the fundamental theorem of algebra is the idea that if we have a polynomial of degree n, then over the complex numbers it has at least one root. And that could be a multiple root. And that's what it's basically saying. There's going to be a root somewhere in the complex number field for every polynomial. Now we know that we've seen ones in the rational field or the real field where we haven't been able to find a root for. Something like x squared plus 1. We know when we look at that we go, well, there's no real numbers that satisfy for x squared to be equal to 1 and make that equal to 0. But we know there's complex numbers there. So that's basically what it's saying. If you've got a polynomial of degree n, then you're going to have a complex number root. At least one of them, and it's going to be a multiple. It could be a multiple one. So, but it's going to have at least one. So, proving that, well, what we're going to do is use induction. So, if we got Sm being the set of polynomial statements, so basically it's a polynomial where n's 1, 2, 3. S1 would be a polynomial of degree 1. So we could write that polynomial as ax plus b, because x is degree 1. It has a 0 minus b on a. So thus S1 is true. So as long as a is not equal to 0, we have that situation. So assume that sk is true, where there's a polynomial degree k that has k roots. So if we consider sk plus 1, then px be a polynomial of k plus 1, there'll be one root that belongs to a set of numbers such that p alpha is equal to 0. So if that's the case, you've got px is equal to x minus alpha q times qx, where q must be a polynomial of degree k. And then we assumed that qx had k zeros, and thus these k zeros must also be zeros of px. So because we have 1 plus k zeros, px must have k plus 1 zeros. So sk is true. So as sk is true, sk1 plus true, and 1's true, must by induction that 2 must be true, then 3 must be true, and so on. So there's a proof by induction of that statement. But really, we just need to be able to remember that we're going to get a root from any polynomial, and at worst, it's going to be a complex root. What we want to do is show another way of proving that the roots of coefficients, roots of polynomials with real coefficients, occur in complex conjugate pairs. So we've got z is a plus ib, and then the conjugate of z would be a plus ib. So playing around with that, we know that we sum the two of them, we're going to get two lots of the real part, and multiply the two of them, we get a squared plus b squared. So when we have x minus z and x minus the conjugate of z, we get x squared minus the sum of the conjugates plus the product of the conjugates, which gives us that one. Now if we divide px is divided by that, the remainder must be less than 2. So in that case there, we get our expression there and divide it into a polynomial px times qx plus a remainder. Because we divide it by x squared, then we must get a situation where that gives us mx plus n, degree at least 1. So again, we break it back down to how we had it before, x minus a plus bi and a minus ib, which is their complex conjugate values, times qx plus mx plus n. So since a plus ib is a 0 of that, we know that that would be equal to 0. So if we substitute it in, we get 0 for the polynomial because we know it's a root. This part would give us 0, and then we get the m times a plus ib because we're substituting in for x plus n. So therefore we get am plus n plus b times m times I, which is equal to 0, which you could write as 0 plus 0i. So for our real and imaginary parts, am plus m would equal 0, and bm would equal 0. So hence m is equal to 0 and n is equal to 0, because b can't be equal to 0, because that would make it, and it wouldn't make it a complex number then. So therefore what we've got to have the situation is that px would equal x minus a plus bi and x minus a minus ib times something, no remainder. So there, p is of a plus ib is equal to 0, and therefore you'll get a minus ib. It would also be a 0 because those two multiply to give us something, their factors there times qx, because there's no remainder sitting there. So there's another proof of that theorem, and why it works. So have a look through. It's a little bit complex, but have a look, and you can see what it's going to work. So let's using all these ideas. Complete the square, factorize this function here. So x squared plus 2x plus 3. And what we're going with the idea of when they multiply, they're going to give us conjugate. So we have x, we complete the square there, so we decompose the 3 into x squared plus 2x plus 1 because we're going to need the 1 there. So it's going to leave us the plus 2. And remember the idea that when we get x squared plus y squared, it's the complex number times its conjugate. So that's where we have x plus 1 minus root 2i, because take the square root of that, and the difference of it. And x plus 1 plus root 2i. So we can see how we were able to use this idea to factorize differently there. And the idea x squared, and if you need more confirmation, x squared minus 2 gives us the root 2 and root 2 there. But with x squared plus 2, we get root 2 and root 2, but it's because it's plus, we need the minus I times the positive I, which would give us plus there in that situation. So in B here, we need to, again, break up the 4x squared plus 3x plus 2. We factorize the 4 out because it's easier to work with a monic polynomial in this regard. So we'll take the 4 out and we have x squared plus 3x times 3 quarters of x, which we get the 3 quarters divided by 2, square it all, gives us the 9 on 64, and the 3 on 4 divided by 2 would give us the 3/8 there. So we get the 9 on 64, which we're going to add to these two terms, but then we're going to have to subtract it to keep it balanced. So that's where we get the half minus 9 on 64, which gives us our 23 on 64 there. This part now factorizes to our perfect square, and we're able to break it up again. The first one minus the second one times I, or square root of the second one times I, and the first one square root of the first one plus the square root of the second one times I, is allowing us to get the difference of two squares with complex numbers in that regard. So another problem here, x equals 1 plus I, which is the 0 of the polynomial. Given that, I'll show it's that, and then factorize it. Well, substitute it in. We're able to sub it in, and it works out to be equal to 0. So take a lot of care with all these terms. They'll all cancel down to give us 0. Now, if we're going to factorize it, well, we do know that if 1 plus I is a root, 1 minus I is a root as well. So, because the polynomial has real coefficients. So we're going to use that idea to help us, because that would expand to x squared minus 2x plus 2. So we've expanded that out. Remember, we're going to use this idea of the x times the x, because they're minus complex conjugates, so we're multiplying by two roots of complex conjugates. We're going to get the x squared minus 2 times the real part of times x, and plus z times its conjugate here. So or the modulus of x of 1 plus I, which is going to give us 2. So expanding it out, we get that one. So, and because it's a cubic, I know that's one factor. So what's the other one going to be? Seeing it's positive 8 there, that will have to work out as a plus 4 for it to be working. So there's our two complex conjugate pairs, or one complex conjugate pair, and the other one will be a real term. Remember when we talked about earlier with complex numbers, when we have this situation, because it's cubed, one root will have to be real, because you can't get 4 complex conjugate pairs or 3 complex conjugate pairs, or you're only going to be able to get 1 complex conjugate pair. So if it's an odd number there, you'll get at least 1 real root. So keep that in mind. So there's that aspect there. Remember, this will help us solve a lot of these problems as we go through, because we're able to go through and use this idea that when we have x minus a complex number and x minus its conjugate, then when we expand it out, we get x times 2 times the real part of z plus z times its conjugate, which makes life a little bit easier when we want to expand that out. So keep that in mind when you're doing a lot of these problems, because we're going to have situations where we're told that one root is, we're given one root and asked to factorize, so we've got to use the idea that its complex conjugate is also a root.